Good afternoon. You can start thinking about this question, and actually, you can even start answering it. I'm not sure about you. My Fridays, the 13th, is just perfect. 2 computers died on me just today. 2. My laptop, my iMac, there is something in it, right? Did I say hello? Okay, just in case, hello one more time. Tension, we know what it is. It's a force inside a string, cable, rope, which is acting on an object attached to it. So here we have an example of a situation when we can choose several different systems of interest. For example, this guy. And for this guy, how many forces are acting on it? There's force of gravity. Well, free body diagram only shows forces. And there is a force of tension. That's the force from the rope acting on the hands. But we also could have chosen system like this. We choose the system. And in that case, for this system right here, the free body diagram also shows 2 forces. And the nature is the same for both forces. There is force of gravity and the tension force. And the third choice, we could have draw a free body diagram for this guy only. Why not? And in this situation, again, that's the object. We can draw the forces. Now, of course, there is a force of gravity. And here, there's supposed to be the tension force acting from the rope on his hands. And also, well, the rope is acting on the same guy. So for this object, for this system, the free body diagram should depict 3 forces. Well, of course, it doesn't matter how we approach the situation, the answer has to be the same. And the answer is, survey says, it's good that you know what tension is. Problem means your life it's not very comfortable sometimes, like mine. We all feel tension sometimes. But If we look at the free body diagrams again, this tension or this tension, which is the same tension acting from this part of the rope on a guy, should compensate, well, one way or another, either two forces acting down if we use this free body diagram. One force is due to the weight of this guy, and another force is due to tension acting down on this guy right here. Or if we use the whole system as one object of interest, and if we draw a free body diagram for that situation, we should draw this arrow, which represents the force of gravity acting on the system as a whole. And if we treat the system as the whole, well, total mass of this system should be equal to the sum of the mass of the guy below and the mass of the guy above. So this is only the weight of one guy. That's supposed to be the weight of both together. And this is the tension which cancels out here the weight of a single guy. And this is the tension which is supposed to cancel out the weight of the whole system. So this kind of reasoning might change our distribution for the answer to this question. So I'm gonna limit the time now to collect the answers, because now we are closer to the answer than we've been before, because we've went through some steps of the reasoning. That's what it is. Friday, the 15th. Please. What are those guys? All right, please tell me, what did you answer? Yes. Okay. $60 kilograms. Tension, gravity. Tension, gravity. G equals 10 in this room. Nothing is moving, everything is in equilibrium. Please tell me what's supposed to be the magnitude of the tension here in newtons. Can't hear you. How did you find it? Well, MA is equal to the net force, which is equal to the force of tension minus force of gravity if we use magnitudes for everything. But it's in equilibrium, right? Motionless. Did you read this word? What does it mean? What does it mean? Motionless. Does it mean less motion? No, it means no motion, right? And no motion means no acceleration. That includes no velocity, but more importantly, for the Newton's law, that means this is equals to 0. So tension has to be equal to force of gravity. And that's supposed to be 60 times 10, 600 newtons. And now here, 90 and 60 is an equivalent of one system with a total mass of what? Please. How did you find it? You add them up, of course, because if we want to calculate the mass of the system, we just have to add up all together the masses of all parts of that system. That word system represents what? What does it mean? What does this word mean, the system? Not everything. Anything. Anything we want to. That's what it means. So every time it's up to us. And if we solve a problem, we have to say, okay, this is my system. My finger points at it. Only after that we can start thinking about forces, writing down Newton's laws. If we don't do this step, we talk about nothing. So we can choose the system any way we like. So this is a new system, and for this system, this force of the tension should compensate this force of gravity. And this force of tension will be equal to what number now? How do you define? See? So if we go back to this slide, what is the correct answer to this question? Will the tension be the same everywhere? The answer is? Say something. I'm giving up on you. No, that's a joke. So please, what does it mean? What does it mean same? And what does it mean everywhere combined together? Here, 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 here. So this number right here for the tension, you told me, equals what? Please. Exactly. We have it calculated. And right here, this number equals what? 1,500, 1,500. So is the tension the same everywhere? Yes or no? That's how we think through every problem in physics. It's just, again, an illustration. All right. So, moving on. Moving on. Another question about tension. What is the weight of this box W? What is the number? Yeah. No? What's the difference between 30 and 300 in terms of the names of what they represent? 30 kilograms represents what? Mass. And this is the force weight, so it has to be mg. It has to be 300 newtons. So again, everything is in equilibrium, so the magnitude of this tension equals 300. And this pulley redirects the tension, but does it change its magnitude? What do you think? This object, this wheel, the pulley, does it change the magnitude of the tension in the rope? No. What's the difference between this case? The tension is the same everywhere. So this, again, the tension which has the same magnitude, 30 newtons. And this situation, when tension changes, there is a difference. Strictly speaking, when we start holding it, we could apply a clamp to it. That's it. That's basically a different rope before and after. We could have just cut it right here, you know, and tied it up to a leg of that guy. Here, the pulley, there is no clamp here or clamp there, which would apply an additional force to it. So here, the tension in the rope, well, changes its direction, but doesn't change its magnitude. So we have 300 newtons down here, we have 300 newtons down here, and to support this system, this pulley, this wheel, should have a force acting up, which will be equal to what number? This force, it has no name, just, I don't know, force acting on the axle. What? 0 would mean it breaks and it falls down. It doesn't break. It holds everything. It holds this weight, and this force must cancel out to these forces pointing down. 600. If we said canceled out, that automatically means that this force alone must have the same magnitude as these two forces combined. Otherwise, it wouldn't be canceled out. And again, so far, equilibrium situation. In equilibrium, the net force acting on anything must be equal to 0. Here, yeah, we have net force equal to 0. Here, we have the net force equals to 0. Well, we neglect its weight. Yeah, it also has some mass, but normally we can neglect it. Moving on, we know what the normal force is. Yeah, that's the force which supports an object and prevents it from falling through something. And this picture shows you that, well, this sack of sand in equilibrium, and the normal force must cancel out the force of gravity acting on it. So the normal force has exactly the same magnitude as the weight of this object. That's not going to be always the case. That's only the case when the object is on a horizontal surface. So here, I'm going to give you "100 seconds. You have to calculate this force, and you have to calculate this force. In both situations, that's the normal force. And when you're done, you should press 1, which says, I'm done. And in 100 seconds, it stops automatically, so. Start. So I'm not sure how it's seen from afar. So here we have I don't know, a book, for example, textbook. Yeah. And we also press on it. So we're exerting additional force. The force we are adding points down and equals 11 newtons. The weight of this book is 15 newtons. Well, we're not strong enough to break the tabletop, so there is normal force which supports it and prevents it from falling through. And that's what the question is about. What's the magnitude of that normal force? And the second picture shows a slightly different situation. So instead of pushing on this book, we attached I don't know, maybe not yours book, maybe your friend's book. You attached a rope to it and try to lift it. And of course, that should change the way the tabletop and the book interacting. So it should change the normal force. Oops. So 90%, that's a very high percentage. And again, everything which happened is just because today is Friday the 13th. So we can close this, we can close this. This is a standard equilibrium situation. In equilibrium, the net force must be equal to 0, which means forces must cancel each other out. So we have two forces pointing down, and one force pointing up must cancel these forces out. That's it. So 11 plus 15 down should be canceled by this force, which means this force must have exactly the same magnitude, which is supposed to be equal to 26 newtons, right? Now here, well, again, it's in equilibrium, so forces must cancel each other out. And here we have two vertical forces, and the magnitude of these two vertical forces must be equal to the magnitude of this single vertical forces pointing down. So what we have here is 11 plus normal force. And again, remember, every time when we write a variable, we must know what it means. And us who set the meaning. And this variable doesn't represent a vector. This variable doesn't represent a component. This variable represents the magnitude. Why? Because I want to. That's it. So it's up to us. We have a lot of flexibility when we solve problems, and we have to use that flexibility in a reasonable manner. And that has to be equal to the magnitude of this force, which is 15. Now we can solve this algebraical equation. 15 minus 11 equals 4 newtons. So the normal force is what we actually measure when we use a scale. Yeah. If I place this box on a tabletop, the normal force prevents it from falling down, and it doesn't matter, I can place it on this scale. The same force prevents it from falling down. So that's what we call the force acting from this plate on this box. That's what we call the normal force. But the force acting back from this box on this plate, which compresses the spring, that's what we call apparent weight or measured weight, more commonly apparent weight. And in this situation, we can see that the apparent weight is equal to the actual weight. The actual weight is mg, but that's not always the case. If I push on it, I change the reading. Now use your imagination. Imagine that you don't see that it's my hand actually pushing. In that case, you think that this is actual weight of this box. That's why we call it the apparent weight. The actual weight is this. But if you couldn't see my hand, you would think that's the weight. And I can apply the force. Yeah, well, I can do it this way. Yeah. If I pull on a string, again, the reading changes. And you may think this is the actual weight, but it's not. So the apparent weight or measured weight, by definition, is that force which is acting on the scale or on the surface. However, the Newton's third law tells us that the normal force acting from the support on an object, and the apparent weight, the force acting from the object on the scale, must have exactly the same magnitudes. So if you have a question, calculate the apparent weight or find the measured weight, that means you have to calculate the magnitude of the normal force because the number is the same. And there are two other possible situations when we can change the apparent weight. Well, for example, imagine that you are holding this scale with this box and you are in the elevator and elevator starts moving up. In that case, what you see, it changes the reading. If the acceleration points up, you start moving up and you're speeding up, the reading actually goes down larger. So the apparent weight increases. But on the other hand, if you start moving down and you're speeding up, you can see the reading decreases. Well, the worst case scenario, if it just freely falls down. Oh. In that case, what's going to happen? Well, the free fall means it falls down with the same acceleration as the scale falls down. So they don't interact actually anymore. So the apparent weight will be equal to 0, and that's what we call weightless. So when an object is traveling with constant velocity, like here, the acceleration of the system is equal to what number? 0. And if the acceleration is 0, we cannot change the apparent weight. It will be equal to the actual weight. Same here. You can imagine that there is a scale here, and the person is looking at the scale and measuring his weight. If motion happening with constant velocity, the reading will be the same as it would have been done at rest. But what is happening if we're speeding up or slowing down this system? Well, there are several examples to walk through to see how it works. In every situation, we have the number which represents the actual, the actual weight of this person, and the reading. Yeah. And we need to figure out what is happening to it. In particular, what is the acceleration of this system? Well, here, the reading is equal to the actual weight. What does it tell us about the acceleration? 0. That's the only case when it might happen. Velocity must be constant. Here, the reading is larger. So how does acceleration point? It should point up. Well, in general, we don't know. So what do we do? Well, Let's draw a free body diagram and let's apply the Newton's second law. We have the force of gravity, which is acting on this person, and it must be equal to 700 newtons because force of gravity is equal to the actual weight. And we have, well, here from the scale on the feet of this person, we have the normal force, F normal. How do I know it's supposed to be longer than the force of gravity? Because of the reading. We know that the magnitude of the normal force has to be equal to the magnitude of the apparent weight, and that's what we read here. So if the apparent weight is equal to 1,000, the normal force has to be equal to 1,000. It's just the difference in direction. The apparent weight, again, a force acting from the feet of that person on the scale. This blue arrow represents the apparent weight. And this red arrow represents the normal force. And the third law tells us they must have the same magnitudes. And now the Newton's second law tells us that m times a has to be equal to, well, let's choose positive direction upward. So the apparent weight has a positive component relative to this axis, plus the actual weight has a negative component relative to this axis, will be equal to 300 newtons. And now if I want to calculate the acceleration itself, 300 newtons times mass. Do we know the mass? Yes? Yes? No, that's not the mass. 70. Again, keep in mind the difference between the weight and the mass. 700 newtons is the weight, but m times 10 is supposed to be equal to 700, so the mass is 70. So that acceleration is indeed pointing upward because the component is positive. Now, here, well, again, for this situation, for the next one, we should have a normal force, and the magnitude of the normal force now is just 400 newtons. So case A, case B, case C, case A, case B, and here case C. I can write the same equation. MA is equal to 400 plus negative 700, which gives me negative 300 newtons. What does minus mean? Well, it points in the direction opposite to y-axis, so the acceleration points down. But the magnitude of this acceleration will be equal to, again, same number, 300 over 70. And here, when there is no reading, that's what we call weightless. That's what an astronaut experiences in outer space. When does it happen? The cable getting caught, free fall. The acceleration of this person is equal to free fall acceleration. And it looks like they touch each other, but they don't press on each other. They don't push on each other. There is no force between the feet and the bottom of this scale anymore. Any questions? Answers? So now we've said about every force on this list, including the apparent weight and measured weight. So what's left? Nothing, just more problems to practice, like this one, for example. How many systems can we choose now? I'm going to ask you this question. I can spend a minute on that. So you just should enter a number. If you think one system, one, two systems, two, three systems, three, four systems, four, five systems, five, six systems, six, seven systems, seven, eight systems, eight, nine systems, nine, and zero means not sure, or more than nine. I can see three immediately, right? And even, well, fourth, so 1, 2, 3, the whole thing always represents a possible system. 4, the question is, do we stop counting? Yes or no? So again, 1, 2, 3, 4. What is the system again? Exactly. So it's important to want more. Otherwise, you might miscount the systems. You have to make the correct choice. Yeah. When we solve a problem, we have to make correct choices for the system, for the free body diagram, for the equation we want to use, for variables we're using, for numbers we plug it in. So physics is all about making the right choices, as well as the life is. We'll see. 6 is the most popular answer. So let's see. We can combine these two together. That's going to be 5. We can combine these two together. That's going to be 6. Can we do anything else? No. So 6 is a correct answer. That's how it works. And of course, some choices are more reasonable, more convenient than other choices. So here, I'm not going to solve the whole problem. But I would always start from a system which composed of all individual parts. In that situation, there is only one force responsible for the acceleration, and that has to be equal to the acceleration times total mass, which is 6. That immediately gives the acceleration. Now, I know the acceleration, and they all travel with the same acceleration. The next choice would have been this, for example. There's only one force responsible for the acceleration of that magenta box. So the force acting on 1 will be equal to the mass of this magenta box times the acceleration, 15/16. The next most convenient choice is this. If we treat these two together as one object, in that case, again, we have only one force responsible for the acceleration of this system, only one force here. Force acting on 2. Well, so that has to be equal to the combined mass of these two boxes, which is 3 times the same acceleration. And by the way, this force from 1 on 2 automatically tells us the magnitude of the force acting from 2 on 1. Yeah. Because according to Newton's third law, they must have, well, same magnitudes. So you see, the right choice of this is, well, there is no right or wrong choices. They're all right. but the convenient choice of the system speeds up the solution. Now, let's talk about situations involving friction. The box is at rest. The mass of this box is 5 kilograms. So we know from the last experiment, if we start applying a force to it, it doesn't immediately start moving. There is a critical force. If we don't apply a force strong enough, it is still at rest. So the question is, what is that critical force equal to? So please solve this. And to answer this question, what do you have to do? Well, among other things, we have to make a right choice. What equation do we want to use? And I'm going to wait a couple of minutes, so you should get your number done. And then, so everybody, please, I insist, take your smartphone, take a picture of your answer, and email it to me. So today, we're going to have 3 sources of your attendance: the attendance sheet, your clicker answers, and your picture. Just for the sake of the timer, you also can press a button. I said 2 minutes. 2 minutes is 120 seconds, but I said it 20 seconds ago, so 100 seconds left. Let's call them. I want to ask some personal questions. 1, 2, 3. So, what equation did you choose? Choose. Yes. Which one? Which one? They're both covering something. So which equation do you want to choose? Pick one. Use it. Maybe it's right, maybe it's wrong, I don't know. But you have to choose and you have to go for it, you know. Especially on the exam. There is no time for thinking on the exam. It's only time for doing. Because it's much better, well, at least grade-wise, to do something than leave an empty space. For something, you will definitely get some partial grade at least. But for nothing, for empty space, you get nothing. That's another test-taking strategy which should be used by everyone. I understand 1, 2, 3. I don't understand 4 and 5. There are only 3 equations, but 5 answers. Okay, I do understand now. Okay. So, most critical pieces of information. Number 1, the mass, 5 kilograms. So, what is it related to? In physics, all variables are related to some other variables. There are no isolated variables. They all related. Maybe directly, maybe indirectly. Mass is directly related to what? Can't hear you. No. We've used this equation today several times. The mass is directly related to what force? Weight, force of gravity, because it's mg. Weight is related to what? Normal force. Mass and normal force are related, but indirectly. So there's a difference between the direct connection and indirect connection. And when we are solving a problem, we're always finding connections from, well, what we know to eventually what we don't know. That's it. Nothing else. Nothing else. We're building a bridge. We're solving a puzzle. And the normal force is related to frictional force, coefficient of friction. Which coefficient of friction should we use for this situation? Static, because it's not moving yet. We need to find that critical force which we still apply and it's not moving, and if we apply just a little bit stronger, only then it starts moving. So if it's not kinetic friction, this equation is gone. Critical means not this, critical means this, maximum value. So that's our equation. That's it. Now we just have to apply it. Now it's a very simple calculation. That maximum force of static friction should be equal to the coefficient of static friction times the normal force, which is in this case equal to mg 5 times 10 times 0.6. What does it give us? 30 newtons. You see? It's all about making the right choices. But making a bad choice better than not making any choice at all. In physics. So now, what do we do now? Now we are applying, okay, same object, same box, same surface, and we're applying the force which is equal to 20 newtons. So, please. Tell me, what is the magnitude of the force of friction acting on this box? No. No. Same box, we are pushing, applying 20 newtons to it. Is it moving? No. If it's not moving, the force of static friction must be what? Opposite end? Exactly. It must cancel that the force we're applying. Everything which is below 30, can't it move? Any force below 30, that's what 30 is. That's a critical force. Everything which below 30 can't make it move. If it's not moving, that means force of static friction adjusts its magnitude to exactly same value to cancel the force we are applying to it. Next situation. Now we are sliding it. So if we slide in it, it's sliding it so well. If we're sliding with constant velocity, what does it tell us about acceleration? What time? So, what does it tell us about acceleration? Keeping velocity constant. Zero, exactly zero. How can it happen? It only can happen if the force which we are applying to it is equal to the force of friction. But now that's supposed to be the kinetic friction. Kinetic. So how do we calculate the force of kinetic friction? That's supposed to be the coefficient of kinetic friction. I didn't hear anything. Times the normal force, which in this situation is equal to mass times gravity, which is 20 newtons. So now, to keep it moving at constant velocity, the applied force also is equal to 20 newtons. I've heard something, did you? Okay. Don't forget, please, that we don't meet on Monday. No matter how you want it to. No, I'm not going to be here. Come back on Tuesday. On Tuesday, we have a regular class. I'm waiting for your pictures. Yeah. And the sign-in sheets over around. I don't see it actually, but someone should have it. Who does have a sign-in sheet? Where is it? Please show me. Here. He took it.
What's the picture for?
The picture?
Yes. Where's the standing picture?
The picture was for this problem.
So
What was the value of the critical force, the magnitude of that critical force we can apply before it starts moving?
Okay. Okay. So just a picture, or
Just a picture.
or also the equation solution sort of thing.
Well, it's a picture.
Okay, got it.
Wherever you put it, it's going to be in the picture.
Okay, thanks.
Yes. Sign-in sheet, picture.
It's never happened before.
Your battery dead.
Yeah. That's what I thought. Yeah, that's what I did all 50 minutes.
I do have around some batteries, but probably the easier way if you just talk to me again on Tuesday before the lecture.
Okay.
And you should send me an email.
I will.
And you should send me a picture with that email
To send you.
of the problem.
Oh, I did.
Oh, you did? Okay. So, but just in case you should send an email, so yeah, I wouldn't forget to bring the batteries.
Okay, perfect. That would be wonderful.
I do have some extras. Yeah, it's just dead battery.
Yeah.
Nothing.
It's old. Okay, thank you. I'll talk to you.
True. But not the red one, only the white one. Yeah, the Ethernet. Yeah, you can take that. Thank you. Yeah. What's that? What's that? What's that? You too. I did this. Great, thank you. Thank you. Have a nice weekend too. That's it. Yeah, well said. You can check on that room, 113.